This video explains topics 9.2 and 9.3, which cover single-slit diffraction and interference. When light shines through a single slit, you can see from this picture that the pattern of light that results on a screen has a central bright area, followed by much smaller bright areas, each separated by a dark spot. Graphically, this pattern of light is shown as a single-slit intensity graph. The x-axis represents theta in radians, and the y-axis represents intensity. When analyzing single-slit diffraction, it's better to think of this small slit as a much larger slit, on which an infinite number of wavefronts are located. Each wavefront acts as a source of waves. Let's consider that rays from each of the 9 wavefronts in this diagram emits a ray at an angle theta to the screen, heading toward point P. Keep in mind that this slit here is magnified, so in fact all of these rays are going to hit a single point. All of these rays are going to travel different distances to reach point P. If you draw a line from the first point source that is perpendicular to any other ray, this distance here is the path difference between them. If we call the width of the slit B, and note that this angle theta is equal to this angle theta, we can say that the path difference equals B sine theta. As we learned in topic 4, the interference between these wavefronts depends on the path difference between them. If two waves have a path difference of half the wavelength, the two waves will destructively interfere and cancel each other out. Since there are an infinite amount of wavefronts, if the first and fifth destructively interfere, the second and sixth will interfere, the third and seventh, and so on. As you can see, at point P there will be no light. This corresponds to a dark spot on our original image and a minimum on our graph. As a rule, we can say that there will be a minimum on the graph whenever B sine theta is equal to n lambda, where n is 1, 2, 3, etc. When doing these problems, because the angle theta is so small, we can approximate that sine theta is equal to theta. Therefore, we can rewrite our rule as theta equals n lambda over b, where n corresponds to the additional minima, n equals 1, 2, 3, etc. If asked to find the angular width of the central maximum, keep in mind that the equation theta equals lambda over b gives the angular measurement from the slit to the first minimum. The width of the central maximum is simply twice this value, or 2 lambda over b. To quickly demonstrate, let us look at the following IB problem. A single slit of width 1.5 micrometers is illuminated with a light of wavelength 500 nanometers. Determine the angular width of the central maximum. Using the equation theta equals 2 lambda over b, and making sure that all of our values are in meters, we can see that the angular width is 0.667 radians, or 32 degrees. Before we move on to double slit diffraction, there are 2 patterns to note involving the slit width, wavelength, and the width of the central maximum. As the width of the slit decreases, the angular width of the central maximum increases. Similarly, as the wavelength of light decreases, the angular width of the central maximum decreases. This same concept can be applied to double slit diffraction. When monochromatic light shines onto a double slit, the following pattern appears. The bright bands are where constructive interference occurs, or where the path difference is equal to n lambda. The dark bands are where destructive interference occurs, or where the path difference is equal to lambda over 2. On an IB exam, you may be asked to find the width in meters between 2 consecutive bright spots. We previously derived that sine theta is equal to n lambda over b, where b is the length of the single slit. We can also say that sine theta is equal to n lambda over d, where d is the distance between the 2 slits. Keep in mind that using the approximation rule, we can say that sine theta is equal to theta, which is also equal to tan theta. If we look at these 2 triangles, we can see that sine theta is equal to n lambda over lowercase d, and tan theta is equal to s over d. If we equate these 2 fractions, we can see that sine theta is equal to n lambda over lowercase d, and tan theta is equal to s over capital D. If we equate these 2 fractions, we get the equation s equals n lambda d over d. You can use this equation to find the metric distance between 2 successive bright spots in double slit diffraction, as well as the width of the central maximum in single slit diffraction, if you treat d as the width of the single slit. For example, let's quickly take a look at this problem. A source of light of an unknown wavelength is used to illuminate 2 slits, a distance of 0.15 meters apart. On a screen a distance of 1.3 meters from the slits, Two bright spots are separated by a distance of 4.95 millimeters. What is the wavelength of light being used? To solve this problem, we would simply use this equation, making sure that all values are in meters, to get a wavelength of 5.71 times 10 to the negative 7th power, or 571 nanometers. When looking at double slit intensity graphs, it's important to note that as the distance between the two slits decreases, the maxima are further apart. Looking at these two graphs, the graph on the top displays two slits with a smaller separation, while the graph on the bottom shows two slits with a larger separation. When considering more than two slits, there are three main trends to observe. As the number of slits, n, increases, the primary maxima will become thinner and sharper. In other words, the secondary maxima become less visible. In addition, the intensity of the central maxima is proportional to n squared. As you can see in this graph, where the number of slits is 20, the central maximum has an intensity of approximately 400. As an overview, from this simulation you can see that as the width of the slit increases, the intensity is modulated by the one-slit pattern. As you increase the distance between each slit, the width of the central maximum decreases. As you increase the number of slits, the maxima become more sharp and prominent, while the secondary maxima become less visible.
Diffraction grating is like double slit interference with more than two slits. The strange thing is that when we add more slits, we get a much more focused picture of the maxima within the interference pattern. Here, I will explain how that works. If we were to draw a line from each of these slits to this point on the wall, we would see that the path difference between each line is 1 lambda. The path difference is represented by each of the yellow lines. Each of the pink lines is what we use to measure the path differences. So as we can see, the first path difference measured from the first line to the second line is equal to 1 lambda. However, if we look at the path difference between the first line and the third line following the pink line, we would see that the path difference between the first line and third line are 2 lambda, and so on.
As we know, the bright points on the wall are due to constructive interference, while the dark points on the wall are due to destructive interference. To review,
the formula to find out what the distance between each slit was, or the angle at which the light was hitting the wall, is through d sine theta is equal to n lambda. Thin film interference occurs when light passes through surfaces with different refraction indexes. The wavelength will go through a phase shift of pi length if the wavelength reflects off of a slow surface. These are the basic things that we need to know about thin film interference, but where are they applied? Say we have an orange light that is traveling through 3 different surfaces. When it travels from surface 1 to surface 2, part of the light will reflect off of surface 2. The rest will continue on until eventually the light contacts surface 3. Again, part of the light will reflect off of surface 3. The light that reflected off of that surface will refract once it contacts surface 2. This will make the two reflections parallel and will also cause an interference when they hit your eye. The colors that you see based off of this interference have to do with the wavelengths of the reflected light and how they interact with each other. Destructive interference will cause the color that the wavelength corresponds to be missing from the spectrum of colors that we see. Constructive interference will cause the color that the wavelength corresponds to be the majority of what colors we see. Whether or not the interference is constructive or destructive will depend on the path difference. If the path difference is an integer of lambda, then there will be constructive interference. However, if the path difference is a fraction of lambda, then there will be destructive interference. This rule changes, however, if there is a pi phase shift. Going back to the idea of a phase shift, if surface 1 was faster than surface 2, and surface 2 was faster than surface 3, then 2 pi shifts would have occurred. Since there were 2 pi phase shifts, however, the rule remains the same. If both surface 1 and surface 3 were faster than surface 2, then only 1 pi phase shift would have occurred. This would cause the rule to change. A path difference of any integer of lambda would become destructive interference, and a path difference of a fraction of lambda would cause constructive interference. The path difference can tell us more than just whether or not the interference will be constructive or destructive. It can also tell us the thickness of the surface that the light reflected off of. The rule is 2dn is equal to the integer of lambda or the fraction of lambda. This is where d is equal to the thickness of the surface that the light reflected off of. N is equal to the refractive index of the surface, and m is any integer.